So I'll get going. All right, so may you live in interesting times. This is generally talked about as an ancient Chinese curse. It's not actually the case. It was like a mistranslation by some British diplomat who was in China in the 30s. The Chinese proverb that he mistranslated was like, better to be a dog in peaceful time than to be a man in a chaotic period. But regardless of where it comes from, it's an interesting concept, and it sort of applies to us now in the multi-core era, since processor power is still going up. Moore's law is still in effect, but to exploit that power, excuse me, we need to use concurrency, parallelism, and if you're lucky, you don't have to share any memory when you do that. If that's the case, you don't need to listen to me. You're done. You can go sit on a beach. But for the rest of us that need to share memory, we need to share it safely. And right now, that generally means either atomics or mutexes. Now, atomics are sort of too fiddly to do anything with, almost. Especially, there's no way you're going to structure a whole program around atomics. It's going to take you a decade, and you probably still won't get it right. They can work in programming in the small, in limited circumstances, by people who know what they're doing, who still have a hard time getting it right. If you have a limited subsystem, you can contain your use of atomics, they can work. So we move up a level in abstraction, and we've got mutexes. They're not too fiddly for programming in the small. If you can keep the whole subsystem you're working on in your head at one time, then you can get them to work. For programming in the large, so you get them to work in the small subsystem, you now want to compose those subsystems to solve a bigger problem. You can't really do that very well due to deadlock. And does anyone here not know what deadlock is? OK, good. I won't bother defining it then. So there's all sorts of strategies to avoid deadlock. And I ask people about this in job interviews, like how do you avoid deadlock? And they give all sorts of things. And you can basically demolish any way that someone is going to try and avoid deadlock. Like you could run into this situation. You have some function, you lock a mutex, you call some other function. Is this safe? Who knows? You got to go look at the source code for some other function and the source code for all those functions. If they take locks, this isn't safe. You could have deadlock. Now let's say you did that and that worked, but now you call some library function you don't have the source code for some reason. It's closed source or it's just too gross to go look at. In this case, you have to hope that it's documented and that documentation is A, not lying to you, and B, actually documents whether this thing takes locks or not. And maybe that'll work for you, but then this happens. Now, you're going to take some function that you're going to call. That function hasn't been written yet. You have no way of knowing what it's going to do. The best you can do here is document your function and ask nicely, don't take any locks. But what all three of these sort of have in common is they destroy your ability to locally reason about your code. You can't just look at one function and decide if it's safe or not. And that's when I say that locks don't compose, that's what that means. You can't just put together small solutions that use locks and hope that and expect them to just work. And really, they're all using what could be termed the asking nicely pattern, and that doesn't scale to large code bases. So what are some alternatives? One thing you could do is use actors, which are also known as CSP or concurrent sequential processes. And that goes back to the beginning where I said, if you don't share anything, then you're golden. With actors, you don't share any memory, and they communicate via message queues. This can work if what you're working on, if the problem that you're trying to solve is structured right and maps onto this concurrency strategy. For everything else, it's kind of inflexible and kind of a pain to deal with. So an alternative to that is transactional memory, which turns out to be a lot more flexible. And before I go any farther, I should probably tell you what it is, since when I ask people this in job interviews or just talking to people, generally they don't know. So to begin with, transactional memory, you have transactions. Somehow you start one. It depends on what your system is. I'll get into details in a little bit. But you have transactions. And these transactions behave atomically. And in this case, atomically means, first off, when you're in a transaction, it behaves as though nothing else is messing with memory. So here I've got an example in thread 1. We're accessing var A, var B, and doing stuff with them. Another transaction on another thread is messing with var A. The first transaction will behave as though that other transaction isn't happening. The transactional system ensures that you see consistent view of memory in your transaction. And I'll get into some ways that that's done in a minute. The second part of atomically is that when you do writes, the writes are not visible to the rest of the system until your transaction is done. And if you can see one of your writes, or if another thread can see one of your writes, it can see all of your writes. So in this case, we have a transaction where we're setting the value of A, and then we do a lot of stuff. And while we're doing that stuff, on thread 2, there's another transaction that runs. It can't see what we've done to, it can't see the change we've done to A yet. And then we get to and then in our first transaction, we then set the value of B, and we finish. And on thread 2, another transaction runs. This transaction can see both, has to be able to see both of those writes. If there was another transaction that ran in between, it might not see it might see the new writes that are done in that transaction instead. But it has to be possible for it to have been able to see, again, concurrency, so the English gets very convoluted. It has to have been able to see what you did. So why do we use transactional memory? So I work for a company named Wyatt Technology. We build these instruments that are used in biotech and pharmaceutical research. And I started there about 9 years ago, and I inherited Dynamics, which was a program that was actually originally developed by a company that Wyatt partnered with. That company went out of business, and Wyatt bought all their intellectual property out of bankruptcy court. And it took me about a year to realize it, but this is sort of the state Dynamics was in. It was falling down under the weight of the amount of data it was being tasked to handle. And really, it was an old program. The original architecture for the amount of data it was supposed to handle was fine. And for the time, it was probably what you would do. Of course, when the company was going out of business, they had hired some contractors who were probably more concerned with getting paid than the future maintainability of the code as well. And so the main problem with the architecture was it used threads, but it only used threads to communicate with the instruments. Once the instruments got data, or once those threads got data from the instrument, it would basically send a Windows message with that data, or send a message through the Windows message queue with that data to the GUI thread. Once it arrived in the GUI thread, that's the only thread that could touch that data. And this leads to problems because if we have a lot of data, we have a lot of calculations to do. The calculations themselves are really short, but if you got 1,000 of them to do, they can take minutes. And if you can only do that on the GUI thread, the program stutters and locks up for 2 minutes. It was really embarrassing. And it also makes it impossible to parallelize the calculations. In a minute, I'll show you that we have a lot of ridiculously easy to exploit parallelism in our data structures. So trying to fix it led to a cascading series of changes that were going to need to be made. I talked about those contractors. The code had a horrible amount of coupling in it. Changing something here meant changing stuff everywhere. And so when we realized this, we were under competitive pressure to get certain features into the software. So we just had to kind of grit our teeth and just go with the way things were working for a couple of years. It was really embarrassing whenever I had to meet customers that use Dynamics. So we shelved making things thread safe and parallelizing things for a couple of years. In the meantime, I was playing with Haskell and their transactional memory system. And for kicks, I said, OK, I want to understand this better. So I implemented a transactional memory system in C++. And in the meantime, I was doing improvements to the Dynamics and constantly finding places where, hey, this would work great with transactional memory. And eventually, I convinced my boss, let's try and use this transactional memory system I wrote in the program. We'll use it in a limited fashion in the data store, maybe storing some experiment parameters, just the stuff we need for the calculations. So if it doesn't work, we can just rip it out and go back to using mutexes. It ended up working really well and kind of took over the whole program. I'll talk about that in a bit. So what does Dynamics look like? So first off, the instruments that Wyatt makes are called light scattering instruments. Basically, you have some sample of something. Usually it's a protein. You dissolve it in solution. You put it in the instrument. The instrument shoots a laser into it. And this is dynamic light scattering. So we look at the light that gets scattered out of it. We look at how that fluctuates and how those fluctuations correlate over time. The faster the correlation dies out, the faster the correlation dies out, the smaller the particle is because the particle's getting bounced around by Brownian motion. And that graph up there is one of the correlation functions. So our data is structured. We have these things called acquisitions, which if you look over in that tree, the tree is full of measurements. And let's see, I can get this thing to work. No, never mind. So the tree is full of measurements. They're all called lysozyme and a temperature because we were measuring lysozyme, which is a protein, and at that temperature. But anyway, so each acquisition captures one of these correlation functions. We do a bunch of horrible math on them. And then we run data filters, and any acquisitions that pass the data filters, we average together the correlation functions to get the correlation function for the measurement that eliminates noise from the experiment. And then we run those calculations on the measurement. Now, in all of those acquisitions are independent. We can run the calculations on those in parallel. Same thing with the measurements. A measurement depends on its acquisitions, but it doesn't depend on other measurements. That's all the easily exploitable parallelism that was really a bummer not to be able to exploit for 2 years. And just to give you a sense of the scope of this, the program's about 800 to 900,000 lines of code. So it's not a huge program, but it's not trivial either. All right, so our system. So this is what our transactional memory system looks like. To start a transaction, you call this function atomically. You pass that a function object. Atomically, in turn, creates a transaction object and passes it to that function. And then when your function is done, whatever it returns gets returned by atomically. Atomically also takes some other arguments that control some optional stuff that I'll get to in a little bit. So I've got an example of a transaction there. This is a pretty boring transaction. All it does is return 0, so result will just be 0. To do more interesting things, you need transactional variables. And I'm going to throw a little jargon at you here. Our system is explicit. You have to explicitly annotate what's going to be transacted, and you do that by storing things in these transactional variables. And here I've created an int and a standard string transactional variable. And in the example, I'm setting the standard string one, or setting the string variable and getting the value of the integer variable. And you can note that we take const references and return const references from get and set. Basically, everything is copied into these objects. And get returns a reference to the stored object, and that reference is good for as long as the transaction is active. If you're going to use that object outside of the transaction that you call getIn, you have to copy it. We can't guarantee that it will still be around after your transaction ends because another transaction could run and replace it. Okay. And our system uses what's called optimistic concurrency. And the way this works is, in transaction 1, we have a transaction where we read a couple of variables, A and B. And then we do a bunch of stuff so our transaction doesn't end for a while. While we're doing that stuff, another transaction comes in and writes to variable A. And it finishes. At the end of our first transaction, we go through we've journaled all our reads. We keep track of everything that's been read. If you read the same variable twice in a transaction, you'll always get the same value independent of what's happening on other threads. That's the memory consistency I was talking about earlier. When you get to the end, we go down that journal, and we make sure nothing changed that you read while your transaction was running. If it did change, we throw away everything you did, and we repeat your transaction. If not, then we've also been journaling the writes, and if you pass the validation, then your writes get published to the rest of the system in an atomic fashion. The one thing to note is we don't validate the writes. If you wrote to a variable and didn't read from it, we figure you don't care about the initial value of that variable. We don't need to worry about its consistency. You just write to. Okay. So one thing is, our system, we have no way of preventing you from doing whatever in a transaction. And one of those things you could do is starting another transaction. In this case, we have two functions here, not a child, which takes a transaction object. And, I forgot to mention earlier, but the only thing that can create transactions is that atomically function. If something takes an atomically argument or a transaction argument, and these transaction objects aren't copyable either, then the only way to call not a child is from within a transaction. But we also have this other function child, which starts a transaction and does something. And now we have a function down here, parent, which starts a transaction. It calls not a child. That's no big deal. That's just a function call. It passes in its transaction object. Nothing weird is going on there. But we also call child, and that will start another transaction. So the question is, what happens when this new transaction commits? In this case, we don't publish any changes to the rest of the system. Instead, we merge all those changes into the parent transaction, and they don't become visible to the rest of the system until the parent transaction commits. There's pluses and minuses to allowing nested transactions. We allow them because we have no way to stop it in our system. There are others. As a Haskell system, you can't actually do this. There are some problems you can run into. I mean, this does allow some more composability in the C++ case. But as I'll show later, there are some problems you can run into with this. So, OK, so that's the basics of our system. There's also SG5. It's not a reference to the old Stargate TV show. It's actually Study Group 5 of the ISO C++ committee. And they're looking at adding transactional memory to the C++ standard. There's a couple of papers there that one of them is a sort of rationale and overview of the system they're proposing. And the other one is sort of the first version of the system. It's a technical specification. It was voted out of committee at the last meeting. So that one's only worth looking at if you like reading standardese. So in their case, you start a transaction by declaring one of these atomic blocks. And they have 3 flavors. There's atomic no except. And the 3 flavors differ based on if you throw a transaction, what happens if a transaction comes out of the atomic block. In the no except case, if a transaction exits that atomic block, you get undefined behavior. The other 2, if you throw the right kind of exception, and actually, sorry, I think I just said throwing transactions, so you're throwing exceptions. In the other 2, if you throw an exception that's the right type, you don't get undefined behavior. And the right type is actually relatively restricted. You can look in the papers. I don't remember exactly. They have to be defined. They have to be derived from certain standard exceptions. But anyway, if you throw the right type of exception out of atomic cancel, it cancels everything you've done up to that point, and just it's like your transaction didn't happen at all. The atomic commit, if you throw an exception out of that, then it commits everything you've done so far. So, yeah. No. Normally you get to the end of, oh, sorry. The question was, do you have to throw a transaction to make your changes visible in this system? Is that a good paraphrase? Or throw an exception, sorry, out of the transaction to make your changes visible. And the answer is no. If you get to the end of the transaction without throwing an exception, then all of these will commit. And there are no restrictions put on how you implement this. You can use optimistic concurrency like we do. You could have one global mutex that you lock, so you can only one transaction can run at a time. I don't think anyone would ever do that. That's basically that's a really convoluted way of writing single-threaded code. And there's also pessimistic concurrency, which works sort of like databases that do row locking for their transactions. You take a mutex. Whenever you access a transactional variable, you take a mutex. Usually it's done by hashing on the address of the variable, and you have a hash table of these mutexes. So you access a variable in the transaction. You take the mutex. You hold that mutex until the end of your transaction. So if anyone else comes in and tries to access that variable, they have to wait until you're done. The problem is if you have 2 threads and they have transactions, they access the same 2 variables but in opposite directions, you have deadlock. So somehow your system has to detect that deadlock and tell one of the transactions, OK, you have to roll back and release all your locks so this other one can make progress. That works really similar to row locking in databases. Everything I've seen, the optimistic concurrency wins out most of the time as far as implementation details go. So in their case, they don't have something like our transactional variable. Their system, to throw more jargon at you, is implicit as opposed to ours, which was explicit. In an implicit system, anything you do inside a transaction is transacted. The one thing you have to be careful with in this is, so we're incrementing I there. If at the same time you're using I outside of a transaction, that's a data race. It's not any worse than having to use mutexes to protect I if you, on one thread, use a mutex and then access I. In the other thread, you don't grab the mutex, you just access I directly. That's a data race. It's kind of the same thing. They have a notion of transaction safety. Because they're modifying the standard, this is going to be implemented in a compiler. The compiler can use the type system to enforce that you only do transaction-safe things in a transaction. And that's basically defined as you can have an implicitly safe function, and that's just a function that doesn't do anything unsafe. Unsafe basically boils down to you don't access anything that's volatile, which basically rules out most I/O. There's a few other technical details. If you're interested in that, you can look in the paper. You can also explicitly declare a function as transaction safe, and if you do something unsafe in that function, you'll get a compiler error. And then an unsafe function is just a function that does something that's unsafe. So then you can see in the transaction, calling the implicitly safe and explicitly safe functions, those are both OK. If you call an unsafe function in a transaction, you get a compiler error. The compiler can statically figure out all this stuff and stop you from making mistakes. That is an advantage of their system. I don't know. I couldn't come up with a way to do this in a library. In Haskell, they use monads. Using monads in C++ is really difficult, and we don't have pure function restrictions. So we just have to kind of live with enforcing transaction safety by policy. They also allow nested transactions, mainly for reasons of being able to compose things easier. They could have made like starting a transaction unsafe, but that leads to some other design decisions that have to be reconsidered. So they allow nested transactions. They work effectively the same as in the system we use at Wyatt. All right, so now the canonical synchronization example. When you learn about mutexes, you use bank accounts. We'll do the same thing here. In this case, we're just doing a simple transfer. On the left, we have what it looks like in Wyatt's system. On the right, we have the SG5 technical specification. In both cases, we have some variables. They're not very good bank accounts. I guess we store cents in there, not dollars. Or we only store whole dollars. And then we have a function that does a transfer from account 1 to account 2. In the Wyatt system, you see we just do a series of sets and gets, passing around the transaction object. And in the SG5 system, it's even simpler. We just have an atomic block, and we use minus equals plus equals like normal. So the thing to remember about this is there's no data races, and there's no way for another thread in the system to see account 1 with the money deducted and account 2 without seeing account 2 having the money added to it. And there's also, if this is implemented correctly, there's no chance of deadlocks. So now I'm going to stick to the Wyatt system because I'm going to talk about some features that we have that aren't in the technical specification yet. And details are still being worked out on that. There's going to be like a version 2 at some point that might include some of this stuff. But let's say we want to send a notification when the transfer's done. Now we could just, so we have a function here, send email. The thing to note about sending email, it's not transactional. You can't undo sending an email. I mean, there are always times we'd like to be able to do that, but you can't. So in our system, the way you handle that is the transaction object has this method called after. And after you give it a function object, and when the transaction commits, it'll be called. After all the validation passes and we've made everything visible to other threads. You could say, hey, instead of doing this T after thing, let's just do send email after the transaction is done, outside of the call to atomically. The problem is transfer with notification here could be in a nested transaction. And then you're back to doing the send email that isn't transactional in a transaction. When you have a nested transaction, we have this list of things to do after the transaction commits. That gets merged into the parents list. And that happens transitively until you get to the top level transaction, and that commits, and then we do all the after stuff. SG5 is looking at something similar. They call theirs on commit actions. They're still working out some kinks in that. So now let's say we want to wait for our account 1 to have a certain balance. In our system, what you do is you just start your transaction like normal. You check the account balance by reading it. And then you call this function retry. And what retry does is it puts your thread to sleep until another thread runs a transaction that modifies one of the variables that you've read. And then it goes back to the beginning and starts your transaction again. Hopefully, eventually, someone will deposit enough money on another thread, and our retry, we'll get our condition there will be above the limit, and we won't hit retry, and we'll do the transfer. Retry also, you can give it a timeout. If it hits that timeout, it throws an exception that hopefully you catch outside the atomically block. And also, atomically, there were those extra arguments that it could take. One of them is specifying sort of a global timeout for any retries that are done within that transaction. If you specify both, it takes whatever the smaller one is. So SG5 is also considering something along these lines, but there are some issues to look out for. I'll show you an example in our system in a bit when I get to pitfalls, which we're going to get to now. So unfortunately, it's not all unicorns and rainbows. It hasn't ever been the case that it's been rainbows and unicorns, which according to Urban Dictionary is really bad. Unicorns and rainbows is really good. So side effects. So this is specific to our system since we don't have statically checked transaction safety. Here I've rewritten our send email or our notification example, but I've taken out the T after, and we're doing the send email in the transaction. So this will work. Send email will be sent at least once, but it could be sent twice, 3 times, 1,000 times, a million times. It depends on how many conflicts this transaction runs into and how many times it gets restarted. So that's why we have to have our after functionality. This couldn't happen in the SG5 system because send email would be non-transaction safe. This wouldn't compile. Yeah. Yeah, so the question is, could we somehow pass the transaction object to the send email and have that check for completion of the transaction and do it? The problem is you still need basically you're just kicking the can down the road. You'd still need to be able to call after in the send email function to be able to queue up sending the email when the transaction commits. Or you'd have to have some other thread that continually watches to see if your transaction is done, notifying it somehow. One thing I didn't mention is transactions and mutexes don't get along very well. In our system, we don't do anything weird under the covers, so they don't play nicely, but it's not impossible. We actually, in the unit test for the transaction memory system, we use mutexes a lot to set up various conditions. In the SG5 system, if you lock a mutex within a transaction, it's undefined behavior. And that also precludes using condition variables, since you can't lock the mutex. Yeah. So, okay. Well, okay, so I wasn't totally accurate. So the question is, it sounds like we don't use mutexes under the covers to implement this. And that's not exactly true. We use a reader-writer mutex. There's one reader-writer mutex. Our system has a really boneheaded implementation that works great for a small number of cores. It's really fast for a small number of cores. But as you scale, it runs into contention. And we need to fix that. I don't know, when there's Core i5s that have like 8 to 16 cores, we're really going to need to fix our system. But right now, we have plenty of performance with our boneheaded implementation. And there are ways to implement this in a mostly lock-free. I don't know how you do retry without locks, but the rest of it you can generally do lock-free for the most part. Okay. All right. So SG5, the send email wouldn't work. Okay. So when we have a function that we know does side effects and we don't want it to be called in a transaction, we can't prevent that statically. But we have this macro called noAtomic, which just declares an argument with a default value. When that default value gets default constructed, it checks to see if we're in a transaction. If it is, it throws an exception that no one can catch and crashes the program. We want to do that because if we don't, we're going to get subtle bugs. So we want to fail fast. It's somewhat heavy-handed, and a static check would be a lot nicer. But this generally has worked for us, and we catch the problems, which are pretty rare, in testing. So a more general, this is sort of something that's general to all transactional memory systems. We don't get deadlock. The big sort of bugbear of transactional memory is starvation. And this happens when we have, say, in this example, we have thread 1, which has a transaction. It reads some value, and then it starts doing a bunch of stuff. Generally, you want to keep your transaction short to keep the chance of conflict down, but sometimes you need to do a bunch of stuff in the transaction. And while we're doing all that stuff, another thread has started, and all it does is continually start a transaction, increment that value. Start a transaction, increment that value. So it's doing that really fast. So whenever we get to the end of the transaction on thread 1, we're going to have a conflict. Unless we get extremely lucky and the thread scheduler in the OS has completely messed with thread 2 and not allowed it to run, we're going to get conflict after conflict, and thread 1 will never be able to make progress. Last year I gave a lightning talk on this, and I said, in 4 years we've been using this, I've never seen this. It was theoretical. Unfortunately, 2 months ago, what? Yeah, I should not have said that, because now 2 months ago I saw this. It wasn't like a deadlock where it got stuck forever. What happened was, in the GUI I showed you, down in the status bar, we show how many things there are left to be calculated. And normally that counts down to 0 and stops. We were encountering a situation where it would start at 600, because it was a big file. It would count down to 0, and then it would go back up to 600 and do all the calculations a second time. And it was starvation. There was a long transaction that was trying to touch every measurement in the system and change something. And while it was doing that, our calculation engine was going as fast as it could, cranking through these calculations, which took a lot less time than touching every measurement in the system. It had something like 600 or 700 measurements, which is a fairly large file, not humongous. Sometimes there's thousands. So it kept preempting, basically, the thing that was trying to touch everything kept getting preempted by the calculations. And eventually, the calculations finished. That's when the counter got down to 0. So then the thing that was going to touch everything would go back and touch everything and re-trigger all the calculations. It would go back up to 600. So the way we handle this, oh, no, OK, I didn't do a slide for that, sorry. The way we handle this is another one of those arguments that you can pass to atomically. You can put a limit on how many conflicts you're willing to have this transaction get. So like you could say, if you get you can get up to 5 conflicts. If you hit that limit, there's another option that says what to do. One thing you can do is it throws an exception, you catch it, I don't know, somehow you then remedy the situation. The other thing you can do is what's called running locked. And when you run locked, I mentioned we use this reader-writer lock mutex under the covers. You actually get what's called an upgradable lock on that. And when you get that upgradable lock, no one else can, and you hold that for your whole transaction, no other transaction can commit. You can still do reads, because read locks can coexist with the upgradable lock. But no one can get a unique lock on that pointer to do a commit until you release your upgrade lock, which you won't do until you get to the end. You upgrade it to a unique lock, you do your commit, and then you release it. It's heavy-handed. In this case, it worked. It was the simplest thing to implement. Other things you can do is basically you can assign priorities to transactions based on how many times they've had conflicts and give priority to ones that have had a lot of conflicts. It's kind of an exponential back-off sort of strategy. It's a lot harder to implement, and like I said, we've run into this once in 5 years, and this solution worked for us. All right, I mentioned there could be problems with retry. So here we've got what I'm going to term a retry deadlock. So basically what happens is you have one transaction. So we've got 2 Boolean transactional variables. They both start out false. In thread 1, we set the value 1 to true, and then we check to see if value 2 is true. If it's not, we retry. In thread 2, we do the opposite. Now, obviously, if these interleave properly, then the setting true of the values will never be seen by the other thread, so they'll be stuck retrying and waiting forever if these are the only 2 threads that are touching these variables. And note I said these are the only 2 threads touching these variables. With a mutex deadlock, if you're in deadlock and some other thread comes along and tries to lock one of those mutexes that you're deadlocked on, then that thread gets stuck too. In our case, if another thread comes along and changes one of those variables, then we'll start making progress again. So it's a softer form of deadlock. It's still something that could happen. This is not actually something that I've seen in real life. This code is kind of structured, is sort of badly structured, and it's sort of basically writing an infinite loop. But we can fix it by splitting this up into two transactions. When you commit the transaction, the other one will be able to see the change to the variable that it's going to wait for. The problem is eventually some bozo will come along and do this. They'll nest those functions that where we split up the transactions into a transaction, and now all the things that we wanted to be in separate transactions are now in one transaction again. So this is kind of, I mentioned there can be problems with nesting transactions. This is the sort of thing that happens. In our case, let's see, oh, I didn't put it. To solve this, I would basically mark the two functions that do the setting and waiting as being not allowed to be in a transaction. And arguably, if you're going to run a transaction and something else is going to rely on the results of that transaction, or you're going to rely on the results of that transaction later on in your function, that's not transaction safe. So it should be marked that way. So this is kind of probably peculiar to our system, and it happens really rarely. But so the example is we've got these two values, and let's say there's an invariant on these values that value 1 is always greater than value 2. And if we rely on that, you can see in thread 1, we have a transaction. We read the value of the first variable. We read the value of the second variable. And then we create a vector that's as big as the difference of those two things. Well, let's say between reading the two values, we do a bunch of stuff. Again, it's a bad idea. You want to keep your transaction as short as possible. But if we can't avoid it, we have thread 2, which comes along. And it modifies both of them. It modifies them both consistently in that it maintains the invariant. Value 1 is still greater than value 2. The problem is we have value 1 from the old values. We have value 2 from the new values. When we commit, the validation will say, no, you saw inconsistent. You have to go back to the beginning. The problem is we're now going to try and allocate probably 4 billion bytes, like 4 gigabytes, and it's going to fail. Arguably, allocating memory is a side effect we shouldn't be doing, but normally it's idempotent. If you use RAII, the memory is going to get released if you roll back, and it's too hard to deal with it any other way. This has happened maybe twice in 5 years, and it's pretty easy to recognize now. The solution is we have this function validate, which we insert right there, and validate basically runs the validation that we normally do at the end of the transaction. It runs the validation then. If your values up to that point aren't consistent, it sends you back to the beginning to try again. We still have to do the validation again at the end because more stuff could have changed. But it ensures that A is going to be greater than B. I've been trying to come up with ways to make this automatic so we don't have to insert the validation. One thing to do would be every time you do a get, you have to validate. But that kind of kills performance, especially if you get a bigger transaction that's accessing a lot of stuff. So this is still kind of an open problem, but it hasn't bit us too many times. OK, so this is more of a design issue, and it's kind of more specific to our system, to an explicit system. But first off, you have to decide what are you going to transact in an explicit system. That's easy. Anything that's going to be touched from multiple threads. The harder part is at what level do you transact things? You can do things fine-grained, where like every member of the structure is in a transactional variable. You could also coarse-grain it by not transacting anything in the structure, but when you store one of these coarse-grained structures, you store a shared pointer to a const coarse-grained. And so when you use that, you get the pointer to the const thing. If you want to change it, you have to copy it, change it, and then shove the new thing into the transactional variable. It all comes down to access patterns, what you choose. If you're going to be reading a lot and barely ever writing, the coarse grain often works better because you only have to make one transactional call to get everything. If you're going to be reading and writing a lot of different stuff on a lot of different threads that are members of that structure, you want to go with the first thing. After a while of working with it, it kind of becomes second nature. In an implicit system, you don't have to make these decisions. How you access things within the transactions kind of makes the decisions for you, and it's kind of automatic. Yep. Sure. Yeah, so, all right, so the question is, how come we don't see a consistent view of memory in this case? The guarantee is that if the transaction commits, I kind of glossed over this. If the transaction commits, then you've seen a consistent view of memory. In this case, that transaction won't commit. If we took out that memory allocation that's going to crash everything and got to the end, that transaction won't commit. It'll get rolled back, and you'll have to try again to get consistent values. And again, this is probably peculiar to our system. I'm looking into ways to make it more automatically catchable. Yep.
What's the exact reason that transaction wouldn't, take the vector of
Yeah.
what's the reason that transaction wouldn't commit?
OK, so the question is, why wouldn't that transaction commit? The problem is, so you read A, and then something else changed A. By the time you get to the end, you're going to have the old value in your journal. The validation's going to check that against what's in A now. It's going to be different, so it's going to say, OK, you have a conflict. You have to roll back and try again. It's because, yeah, that's what causes the conflicts. If you read something and it changes before you get to the end of your transaction, then it's a conflict and you have to try again. Mm-hmm.
So the issue there is you've got an invariant between two
Yeah.
variables, and you read them at different times, but that's not what causes the transaction fail. It's not the fact, because you don't actually have in your system
Yeah.
any knowledge that that invariant is not expressed anywhere.
Yeah, the transactional system doesn't know anything about the invariant. That's something you have to enforce in your own code. It would probably, actually, one strategy, now that I think of it, would be to somehow express those invariants in the system so the system knows, like, when you read this, if this changed, you have to, it's already a conflict. That's actually something I'm going to have to look at. What? Well, not necessarily. It would just be that, yeah. Well, it would just be, so we've read A. When we read B, if we've expressed some sort of constraint between them, then when we read B, when we read either of them, it'll check if we've already read A and then we read B, it would check the constraint. And if the constraint is violated, it knows, OK, something's wrong here, roll back and try again. That would prevent you from having to do a full validation. Hey, I'm glad I gave this talk. Now I got an idea to pursue here for this.
It's like, oh, we're never going to be able to commit to a transaction. We can actually afford it.
Yeah. Yeah. OK, so let's see. OK, so we got 5 fine course. OK, so weak atomicity. Basically what happens here is you've got this transaction. You pull something out. In this case, you're flying down the trench. You pull out an exhaust port. Once you have that outside of the transaction, you can do whatever you want with it. You can do stuff to it that is not transactional if it's not structured properly. In this case, we're going to shoot a proton torpedo at it. That's not transactional. So we have a weakness. In our case, we handle this by requiring that everything we store in transactional variables is either immutable or internally transacted. Immutable is basically the coarse grain thing we saw before. You can't change it. To update it, you have to get it, copy it, make your change, and then put the copy into the transactional variable. The other thing to do is internally transacted, and that means any mutable state in the structure has to be transacted. It either has to be in a transactional variable or you access it through a transactional function, which will, underlying that, will probably just be accessing transactional variables. This we enforce through code review. I don't have any way to enforce this statically right now, but it's generally good. Sometimes we get new people who decide to start const casting things, and that's a problem. But if they're const casting, that's not going to pass code review anyway. OK. So another pitfall is, this is more philosophical, it can be really invasive. Remember at the beginning I said, OK, we're just going to apply this to the data store and some parameters and stuff we're using in calculations. It worked so well, it took over the whole core of the program. It worked really well, and it's a lot easier to interface transactional code with transactional code. Interfacing transactional code with non-transactional code, you have to use the after stuff and deal with function objects and think kind of it's non-linearly. This is going to be executed at some point in the future. So really, the stuff that isn't transactional, our GUI's written in MFC. You can pity me if you want. I would love to change that, but I don't have that much time. So obviously, that's not transactional. It calls into the transactional code and starts transactions, like the message handlers can start transaction and everything, but it's not transactional itself. So we have to use afters to trigger things there. In fact, one of the big side effects that's usually really obvious that newbies make is they pop up a dialog box from within a transaction. That dialog box pops up maybe once, maybe twice, maybe 1,000 times. And then we say, okay, no, you have to use after here. The other thing we have at the other end of the program, we have some code that has latency requirements, mainly getting data from the instrument. If we don't get the data fast enough, pull it out of the socket fast enough, the instrument will say, okay, you're disconnected, you're not keeping up. And some of our data, we're moving quite a bit. So probably the last thing here is no one's heard of it. When we go to hire people, I'm interviewing, I say, oh, have you heard of transactional memory? And most people have not heard of it. If they have heard of it, they've never used it. It's not a big deal. Generally, you come up to speed pretty fast. It takes maybe a month before they stop making dumb mistakes. Or newbie mistakes. That's not fair, dumb mistakes. Newbie mistakes. They haven't ever used it before. It's not fair to call it dumb. But more importantly, since no one's ever heard of it, there's no best practices out there. There's tons of academic papers on how to implement transactional memory. There's nothing out there on how to use it. So we're kind of figuring it out as we go along. It's worked out pretty well for us, and I think that's just, it's easier to use than locks. We find cases where we have to figure things out, and that's actually kind of fun, because we're kind of working on the frontier here. But that's kind of it for pitfalls, unless you consider performance a pitfall, which some people do for transactional memory. And what I'll say about performance, just kind of as a generalization, it's kind of like this car. In the right conditions, it's great. It's not going to beat a dragster. It's not going to beat a Formula One car, those being Mutexes or Atomics or something, in the conditions where those things excel. If you put a Formula One car on a dirt track, this car's going to destroy it. So specific to our system, so first off, dynamics, it's not really a low latency application, modulo what I mentioned before about instrument communication, where we don't use transactional memory. It's not a game, it's not a trading bot. We don't have hard real-time requirements for the most part. The other thing is we're really good at hiding our latencies that we have. We push as much as possible on the background threads. And the transactional memory makes that really easy. The GUI, as much as possible, we don't want it to lock up. If you're going to do something that's going to take more than 10 milliseconds or whatever, put it into we have a calculation engine that you can put it in as a high priority thing so it'll get done as soon as possible, whenever a thread's free to do it. And part of that is also we prioritize things in our engine. If you're looking at a specific measurement, any calculations related to that get priority in the calculation engine, as long as there's nothing really high priority that the GUI needs done. So even when we have latency, it's in there. Also, our calculations are almost ideally set up for transactional memory. There's the next slide, I'll get into what that means. As I mentioned, some instrument communication is low latency or needs to be low latency, so it doesn't use TM. So with those caveats, we get plenty of performance. And our calculation structure schematically looks like this. We get some parameters, we get the data, we do a bunch of horrible math that takes a long time, relatively, it's a couple hundred milliseconds maybe. And then we store the results somewhere. The only parts that need to be transacted is getting the parameters, getting the data, storing the result. The calculations is basically, it's a pure function in the parlance of functional programming. It doesn't need to be transacted. And so the calculate result, the amount of time that takes totally dwarfs any overhead we get from the transactional system. Okay. So more generally in performance, it's probably never going to be as fast as a hand tune using a Mutexes or Atomics. There's just more overhead. You have to validate, in some way you're going to have to validate your journal, or you're going to have to be dealing with these Mutexes in a pessimistic system. And there's also a bigger non-deterministic price to pay when you do have contention. So when you have contention with Mutexes, you're coming along, one thread's locked in Mutex, it can go on its way, another thread comes along, it tries to lock the Mutex, it has to sit there and wait until the other one's done. You pay a little bit of penalty there, waiting for the Mutex to be unlocked. In our system, both threads will just blaze right on through. One of them will commit, the other one will have to go back and start again and repeat everything it just did. So that's a bigger price to pay. If you're using a pessimistic system, you'll have to wait on locks, and hopefully you don't get deadlock and have to roll back and do that. But there are cases where you can have less contention. Here I've got an example. We've got two variables that we're going to use, A and B, and we're only going to use them in a read-only fashion. To safely use A and B, because other threads might be writing to them, we have to lock a mutex in the mutex case, and we have to hold that while we're using A and B. So only one thread can be running use A and B at a time. In the transactional case, we read A and B, we aren't holding any mutexes, and we have to hold a mutex while we're reading them, but we release it right away. So there's a lot more concurrency that's available there. Any number of threads can be running use A and B concurrently. This is a little artificial. You could say, well, let's use a reader-writer lock in the mutex case, or you could restructure it to not have to hold the lock the whole time. But notice I'm saying change this, change that. It's automatic. It automatically happens in the transactional system. In the mutex system, again, non-local reasoning, you have to figure out how your mutexes all relate to each other. So in some ways, you can get better concurrency in some cases. And sort of ancillary to performance, whenever performance in transactional memory comes up, people mention hardware transactional memory as like, this is going to save everything. And this actually exists today in the form of Intel TSX. It was in the Haswell processors, but there was a bug in it, so it got disabled. It's currently in, I think, the high-end Broadwells. I don't know if that means Xeon or the high-end Core i7s. Intel's kind of seems to be kind of cagey about it. I haven't looked into it super deeply because we can't really use it right now for our system. But from what I have been able to find, and it's going to be more available in the Skylake processors. So this system, first off, it transacts cache lines. What this means is, say you have two variables A and B that are on the same cache line. You could have a transaction that reads A, and you have another transaction that writes to B. Even though they've written and read different variables, that'll be a conflict. It's also implicit, like the TS system. There's an assembly language instruction that you omit that starts the transaction. From there on out, everything you do on that processor core is transacted. And then at the end of your transaction, you omit another instruction to either commit it or abort it. If you commit it, it tells you, OK, you committed OK or not. And then the other thing is, this system is bounded. And first, let me define what unbounded means. The TS system and the SG5 TS system and Wyatt system are both unbounded. You can do as much transactional stuff as you want in a transaction. If you do too much, it's a bad idea because you'll probably get conflicts. But you can do whatever you want up to the limits of memory or address space or whatever, and it'll work. In the TSX system, basically there's a read buffer and a write buffer that stores these cache lines that you've accessed transactionally. They're of limited size because you're on hardware. If you spill one of those buffers, you can't commit your transaction. It's just done. You can't do anything. So you either A, have to be working in a domain where you know you're on this hardware, you can arrange everything, you're programming in the small, you're looking at the system, you can arrange that you know you're not going to spill those buffers. And if you do, it's a bug, you have to go in and fix it and rearrange things so that you don't spill the buffers. If you can't do that and you want to use this, then you have to somehow fall back on a software system when this happens. And I suspect when we get implementations of the TS, someone will probably try and use TSX and create a hybrid system where when they can, they use the TSX stuff, and when they spill the buffers, they fall back on the software system they're going to need anyway when they're running on a processor that doesn't have TSX. As I said, we currently, I haven't tested this or tried anything. This is all just based on reading Intel's white papers. The implicit kind of causes us problems because our system is explicit and we rely on that. And the bounded means just that it would be more work to implement behind our system. OK, so how did it work out? The TLDR of the talk, which normally I probably should put at the beginning, but we'll put it here. It worked great. You just have to keep in mind all the stuff I told you about, how our app is structured, what kind of stuff we do, so that you can understand the performance profile and how it fits in. New people get up to speed quickly. I mentioned no one knows about it, but they come up to speed pretty quickly. It's relatively easy to use. It's much easier to reason about than locks, which, it's more fun than mutexes, really. Mutexes are fun when you have a small system and it's a puzzle to figure out how to lock them and make sure that everything works without deadlock. It's not fun at the big things. So we have another team that works on another application that's similar to Dynamics. It's a little bigger. It works with different instruments. They're using mutexes because they weren't in the state where they were going to rewrite the core of the program. And they're just, they're looking for deadlocks all the time, and it's no fun. So really, it kind of optimizes for programmer time. We don't have to hunt down deadlocks all the time. Every once in a while, there's a weird issue, but it's way less work to track them down than deadlocks and dealing with mutexes. So before I open up to questions, last year, of course, the first question was, is this open source? Can I play with this? Last year, the answer was no. Sorry. This year, the answer is soon. A couple of weeks ago, me and my boss convinced the Wyatts, the people who own the company and run it, hey, let's open source some stuff, give back to the community. We use a lot of open source stuff. So we got permission to do it. So far, all we've done is come up with a license. It's going to be some form of BSD license. Since I've been preparing for this talk, we're also trying to get a big release out. I haven't had time to clean it up. There's some embarrassing code in there that I don't want anyone outside the company to see. So, open sourcing, it's already improving the quality of our code. It also, it's got some Windows-specific stuff in it dealing with thread local storage that needs to be made cross-platform too, I think. There's also some other goodies in there. We have basically a transactional version of futures, not everything that's in futures, but something similar to futures. We've got multicast channels and queues and some other stuff. To find out when that happens, you can watch my blog, which is that top link there. It's also, if you go to my bio on the schedule, there's a link there. If you want to know more about Wyatt and what we do, there's Wyatt.com. If you're starting a biotech company, you just got a ton of funding and you want to buy a bunch of instruments, go there, get in touch with our sales staff. Mention that I sent you, so maybe I'll get a bigger bonus next time. If you want to know more about the SG5 system, there's papers. There's N3919, which is sort of the motivation and the details of their system, and N4514, which is what actually got standardized. There's some differences between the two. So if you really want to know what's coming with that, you have to dig through the standardies in 4514. I also wrote a paper for them, 4438, that just details our experience using transactional memory, how our system works, and what we found to be useful and not useful. It's a lot of what I talked about here. It goes into more detail on stuff I glossed over, and there's stuff I didn't mention that's in there. So if you want to know more about our system, that's actually a good source. My blog, I write stuff a little bit. I was going to write a lot on the blog, but then this Michael Wong, who runs the SG5 group, asked me to write this paper for him. And that sucked up all my time. And I figured, you can just go look at the paper. So there aren't any implementations of the SG5 system yet. They're working on one. I know one is in process on GCC. I don't know what the status on it is. I think it's just, the person who's doing it just started on it. There's also talk of doing one in Clang. But GCC has had an experimental transactional memory system in it since 4.7. I'm not sure exactly. I haven't played with it, so I don't know what you have to do to enable it. I don't know if you have to compile GCC from source and give it a compiler flag, or if it's just in there and you just turn it on with a flag on the command line when you compile your own code. It's similar to the SG5 system. It's not exactly the same. And that's why GCC will probably have the technical specification before anyone else, because it already has this system that they can build on. Intel had an experimental compiler that did transactional memory in a way similar to the SG5 technical specification, but it's been retired. It was actually around when I first started playing with this stuff, but it was labeled very experimental, and it's an experiment we didn't have source code for, so relying on that in our production application would be a bad idea. Instead, we went with my system, since we had the source code and we had the guy who wrote it on the payroll. But I'm not sure if you can still get that, but that's something else you can look at. And with that, I guess I'll open it up to questions. Oops. Okay, over there. Uh-huh. Uh-huh.
Or like fine grained or coarse grained, and that standard does it implicitly. I mean, does it have some really clever mechanism of finding out, or does it do everything fine grained?
So the question is, in our system, it's explicit. There's this notion of fine grained versus coarse grained, and in the TS, there isn't that because it's implicit. So I kind of glossed over it, but how you access things is going to determine if it does fine grained or coarse grained. If you're always like grabbing a pointer to a const object, somehow transferring that out of the transaction and using that, then you're basically coarse graining. If you're constantly inside the transaction, inside the atomic block, accessing the member variables, then you're fine grained. It sort of happens automatically by osmosis, how it works. There isn't anything different that the system does. It isn't trying to detect how you're doing this that I know of. I mean, well, none of this has been implemented yet, so I mean, conceivably they could do something like that. But I don't think they need to. I think it's just how you access things will determine how things get transacted. Yes?
In your system, do you have a sense of how many CPU cycles are wasted in aborted transactions?
So the question is, do we have a handle on how many CPU cycles we're wasting in aborted transactions? I don't. I have some really rudimentary profiling built into our system, but it's more based around on figuring out what's conflicting with other things. I haven't really looked at it. It hasn't been noticeable. I'll give you that. But again, our system isn't super performance heavy. I mean, we want the calculations to go as fast as possible. But when we're talking about, like, you're calculating 1,000 things, and each thing can take half a second. I mean, it's horrible math. It takes that long. If the scientist who's waiting for these results has to wait 30 more seconds, they aren't going to care. And the GUI is going all the time. We hide these latencies. If you're looking at something, it will get calculated first. You won't notice that it's still calculating all this other stuff. Most likely, they're down the hall getting coffee while this collection is going on and things are being calculated. And they'll come back in a couple of hours, because doing the actual collection takes a long time, because usually you have to wait for temperatures to change in the instrument and do all this other stuff. So yeah, I don't have a good answer for that. Yes? Uh-huh. All right, so the question is, what do we do with more complicated structures like vectors and maps? One of our main data types is called the correlation function, and it's basically a vector of 512 doubles. Okay, so this is going to be the last question. When we store that, we store a shared pointer to a vector, and most of the time that never changes. For the measurements, it does, because we have to average the acquisition correlation functions. And in that case, we allocated a new vector inside a shared pointer, and the shared pointer is to a const vector. That's really important. You can't change the vector once you've put it into the transactional variable. In other cases, instead of using the standard map, there's a book by Chris Okazaki, which is about functional data structures where they're persistent, but they're immutable. So basically, copying them is extremely cheap, and then when you modify them, you're basically copying them, but you're only changing the nodes, like in a tree, you're only changing the nodes that are affected by the thing you're inserting. And we use that. I mean, mostly, you want to use vectors for everything, and so you use shared pointers to const vectors a lot. That answer is kind of weird. And for more complicated things that might have links inside, again, those things are going to be const. So and you're going to store within them. You're either going to make those things immutable by storing a pointer to a const object, if it is allocating memory for something, or I mean, these are within your own structures that you're defining, not in like STL stuff. Or those things are going to be stored in transactional variables within your structure for the internal transacting. Okay. I don't know. Well, maybe see me after. You can ask me. Okay. Thanks, everybody.